In this chapter, we're going to talk about how forces influence the motion of an object. So, what is a force? What's a force? What is a force? Force is a push or pull. When we push or when we pull an object, we can change the state. For example, if we push a an object uh, traveling at a constant speed or velocity, because of that additional push or pull, we can change its motion. What will happen if you push an object when it is moving at a constant speed? Due to that push, we can accelerate the object. So because of the force, we can change the state. If there's an object at rest, if we apply a large force, we can move that force. Or if an object moves at a constant speed or velocity, because of this force, uh, we can change its acceleration. So in the second part of this chapter, Newton's laws, we're going to discuss what will happen to the motion because of this force. Contact forces and non-contact forces or action at a distance force. Contact forces, let me draw a object, a large object, and we can tie a rope onto this object and we can apply a force and we can move it. If you consider like two magnets, let's consider a magnet 1, and let's say this is north. So we know that if we bring two similar uh, polarities together to a magnet, those two repel. So again, we have a force, magnetic force or repulsive force, but there is no contact. Here, if we want to move this object, we have to have a rope, which means it's contact and needs to apply, or we have to push it. So again, we have to have a contact force. So uh, the the result is same, but one is contact, the other one is non-contact. So last week we talked about vectors, and force also a vector, which means it has a direction and also it has a magnitude. So when we represent or when we draw a force, we need to draw a line along that force, and we need to have a arrow which represents the uh, direction. Direction and also magnitude. So with direction and a magnitude, we know it's a vector. So force also a vector. So we use uh, arrows to represent forces, and also length represents the magnitude. And we also know how to add forces or how to add vectors. If the vectors are in the same direction, we can add vectors just like scalar numbers. But if they in a special angle, then we have to there are a couple of different techniques. We can use geometry, or we can draw it to a scale and then measure the net vector or resultant vector. Or we can also, we learn another technique, component addition. We can uh, split, or we can separate the x component and y component of each vector, and then we can add x component of those vectors together and y components of those vectors, and then finally you have two vectors, one in x direction and one in y direction. So once we have two vectors which are perpendicular to each other, we can easily calculate the resultant vector. So mass is a measure of the amount of stuff. What is stuff? Amount of stuff contained in an object. So every object we know made out of atoms. So if for a given object, we can say how many atoms in a given object. And if we know the mass, or if we know how many atoms in there, we can calculate its mass. So mass is just a number like 10 kilograms. So 10 kilograms, it has a magnitude and a unit, but there's no direction. So therefore mass falls into a scalar. There's no direction. Amount of stuff of an object, we call it mass. So Newton's first law. Actually, this law has two subsections, or this law we can split into two separate sections of an object. If an object at rest or moving with a constant velocity or speed. Constant velocity. So if an object at rest, that's the part one, if an object at rest remain at rest if there is no net force. If we apply a force onto an object, if the force is large enough, we can move the state. So at rest is one state of an object. And the second state is if an object moving in a constant velocity. If we apply a additional force, we can change the speed, or we can change the velocity. So without a net force, we cannot change the state. Either it's at rest or remaining at constant velocity. So Newton's law is an object continues in a state of rest or in a state of motion. At rest or state of motion at a constant speed along a straight line, unless there is no net force. If there is no net force, if an object at rest remain at rest, or if an object moving at a constant velocity, it maintain that velocity. What is net force? We already know how to calculate the net force of an object. I'm going to show you a few more examples so that you can thoroughly understand the meaning of net force. So let's say this box on your left side has two forces acting on it. 10 Newton force. Newton is the unit of force, and when we derive a first equation for Newton's law, we will talk about how we get this unit, but Newton is the unit of force. So this box has two forces acting on it, 10 Newton to right and 4 Newton to left, and we know how to add vectors. We can draw one vector from tail to head, and then we bring the other force, tail of the second force, and draw in the opposite direction because it's opposite direction. One is 10 Newton. The second force is 4 Newton. And now we know how to calculate uh, tail of the first force, head of the first force, head to tail of the second force. And the net force is tail of the first force to head of the second force. So I didn't draw it to the scale. So 6 Newton. This is your net force. So you can draw it to a scale, or you can draw and you can estimate, or you can calculate the magnitude of the net force, or result. We call it net force or resultant force. If there is no net force, if an object, according to Newton's first law, if an object at rest, if it is not moving, if there's no net force, it remains at rest. If an object moving with a constant speed or velocity, if you apply a net force, we can change the state of that motion. Here's the second example of net force. In this case, one force is 4 Newton force is to your right, and the second force is move in north direction. So again, if you want to add these two forces together, you can draw a similar tail to end diagram. We always draw, when we add vectors. Let me draw one vector. Let me draw the horizontal vector 4 Newton to this direction, and then you bring the other vector 3 Newton vector, and your resultant force is, this is the tail, head, tail, head, tail of the first vector to this is your net force. So you can calculate the net force, square root of 4 square plus 3 square, and it's 5 Newton. And this angle you can use, this is 3, this is 4, tan theta. If this is theta, tan theta is opposite over adjacent, and then you can calculate theta, then you will get this angle. So 64 degrees with respect to your horizontal direction, and the magnitude is 5 newtons. So we're going to talk about another new term, inertia of an object. So inertia is like a natural tendency of an object to stay at rest. Naturally, objects like to stay at rest. So mass of an object is a quantitative measure of inertia. Higher the inertia, higher the mass. So natural tendency of stay at rest, and standard unit of mass is kilograms. So mathematically, the net force is written as sigma F. Let me give you an example. Let's say I have a force F1 and also another force F2. F2, I have a F3, all forces in one direction. F4, F5. If we want to get the net force, F is equal to, we add all of them because they are in one plane or one along one direction. So F1 plus, F2 plus, F3 plus, 4 plus, F5. Rather than write down F1 plus F2 plus F3, we know F3 is in right direction, but it's the magnitude, so when you apply the force, we can change this sign. So F4 plus F5. So rather than F1, F2, F3, F4, and F5, we write a notation for the force. F is sigma F. Sometimes you can see Fi. So all these are vectors. So I means 1, 2, 3, 4. Sig and phi. Sigma means addition of forces. So rather than write down F1, F2, F3, F4, and F5, we can write this implies F1 plus F2 plus F3. So summation means sigma, F means force, and I means how many forces. Here I equals 5. So instead of write down all the forces, we can write a notation sigma F. Sigma represents summation, sum of all forces. Okay, we're going to move on to Newton's second law. First law we describe due to external force or net force, we can change the state. If an object at rest remain at rest unless there is no net force, or if an object moves in a constant velocity, we can change the velocity, or we can change the state by applying a net force. In Newton's second law, we're going to describe how force influences the acceleration. Before we go to the second law, let me give you an example. Let's consider a mass M. We have a mass M. I am going to apply a force F onto this mass, and because of this force we can let's say this is at rest, initially at rest. Because of this force F, we can accelerate this object. Accelerate is we can change the state. So now it's moving. So let's consider the same mass M, and now I can double this same mass, but I'm going to double this force. Instead of 1, now I'm going to apply another force. So now we have two forces acting on the same direction on the same mass. If we double the force, we can double the acceleration. If the force is double, initially it's F, now it's 2F. If we increase the force on the mass, we can change the acceleration, or we can change the speed. If you add another force, third force, we can even increase the acceleration. So which means force is uh, directly proportional to the acceleration. So acceleration I can write proportional to force. Force is this is proportional to force. Acceleration is proportional to force. So if you increase the force, acceleration increase. If you decrease the force, acceleration also decrease. So if you do uh, increase or decrease, acceleration also increase or decrease depending on the force. Let me go to a different example. Let me going to keep the same force F, and if we increase or decrease the mass, let's talk about what will happen to the acceleration. I'm going to keep the same force F, and again I'm going to take two examples, mass M. Okay, and the second case, I'm going to double the mass. I'm going to stack another mass on top of this M. If it is 10 kilograms, this is 20 kilograms. Same force F. These identical forces, but now we apply on 10 kilogram mass and 20 kilogram mass. So we know mass is inertia, tendency to move. So if you have a higher mass, even though the force is high, you know, force is smaller compared to this scenario. So therefore, uh, if you apply what will happen to the acceleration? So I can write acceleration is inversely proportional to mass, which is a opposite relationship. In this previous case I discussed, if we decrease one parameter and the other side also it decrease. Here if we increase the mass, acceleration decreases. Here 10 kilograms, here 20 kilograms. So if I increase the mass, uh, higher the mass, it moves or it has a small acceleration. So therefore we call it, it's an inverse relationship. So if we de decrease the mass, acceleration increase. Therefore, it's an inverse relationship. So now I can combine uh, the acceleration proportional to force and acceleration inversely proportional to mass into one equation, and I can write acceleration is a vector is proportional to force over mass. Actually, this is Newton's second law of motion. You don't need to learn how to do. So this is the second law of motion. Acceleration is equal to net force divided by mass. Or you can rearrange this equation and you can write net force is equal to, which is a vector, mass times acceleration. When a net force acts on an object of mass m, the acceleration that results is directly proportional to net force, which we talked about in the previous chapter and previous slide, and has a magnitude that is inversely proportional to the mass. The direction of the acceleration is same as the direction of the force. So force acceleration is a vector, therefore force also a vector, because mass is a scalar, no direction. So direction of the force is exactly same as the direction of the acceleration. How about the units? So unit of force is unit of mass times unit of acceleration. So unit of mass, SI unit of mass is kilograms. Units of mass is meters per second square. Therefore, unit of force is kilograms meters per second square, which we call Newton. When we talk about Newtons, we need to know that Newton has kilograms because of the mass, and also meters per second square, which is acceleration. So force is mass times acceleration, units of mass times units of acceleration. So kilograms meters per second square, we say it's Newton. So inside Newton it has kilograms meters per second square. Here's the slide of units of mass, acceleration, which is equal to force, unit of mass, unit of acceleration. The combination, we call it Newton. Free body diagram. Free body diagram is a sketch which represents the forces acting on it. So you can see a figure of a car and two-person pushing that car. So rather than drawing everything, to people and the car and the forces, you can just represent the car with the dot like this, and then you can write two forces. One person pushed the car with 275 Newton. This is your force 1. And then same direction there's another force, a little bit larger force, 395. And also you see another force in opposite direction. You see another force opposite direction, F3, 560 Newton. Sometimes we call it friction. We will talk about friction, the force against the direction of the motion. So every time when you push or pull something, there's a force, we call it friction, opposed to that force. But these three forces in the same direction or same 2D line, and therefore we can add F1, F2 and F3, and we can calculate the net force. So in free body, we don't have to draw the car and individual, but you can represent like a dot, and then you can draw the forces with arrows and a line with the magnitude, and which represents exactly the same idea which this picture shows. So three forces, two forces to right and one force to left, and this dot represents the car. So instead of drawing everything, you can just draw a sketch. We call it a free body diagram. Here it's shown that how to calculate the net force, the total force, two forces to right, 275 and 395, one force to your left, which is the opposing force. Therefore, you have a negative sign. So if you add these two, you can add these two together and subtract that. You end up with a plus again, which means it's the major of the force. It's to your right magnitude, and this plus represents the direction, which is to the right, and we call it net force. And when you calculate or when you use the Newton's law, second law, to calculate, you have to consider the net force, which is the total force acting on an object. Net force. So in the same example, we learned that Newton's first law, net force is equal to mass times acceleration. And in this example, it asks you to calculate the acceleration. Acceleration you can solve net force divided by mass. In the previous slide, we calculate the net force plus 110 newtons divided by mass. We get plus 0.059 meters per second square. Meters per second square is SI unit of acceleration. Plus means it's in um, right direction. In previous chapters, we learn how to write kinematic equations in one dimension and two dimensions. We basically use the one dimension equation and then add a subscript x or y to represent the motion along x direction and motion along y direction. And similarly, we can modify this Newton's second law along x direction and y direction, and we can write two equations instead of one general equation. So we're going to add subscript for force. Force is a vector, therefore if you specify a specific direction, this force along that direction, and this acceleration, we can add another subscript x or y. So if force is x direction, acceleration also in x direction. If the acceleration is in y direction, force also in y direction. So basically this equation we can write two components. Y component, net force along y direction. This is net force along y direction, which is equal to mass, no direction. So and then acceleration along y direction, net force along x direction, acceleration along x direction. So every time when you use Newton's laws, again you have to consider the direction it travels, and you have to use the direction force in that given direction, and also acceleration also in the same direction.